Okay, then we will start. Yeah, we will start with our talk of today, which is by Dimos Tsouros. So Dimos works on constraint acquisition. He did his PhD with Costa Steriou in University of Western Macedonia, and he's basically I think he's on a mission to modernize constraint acquisition and to take it into new directions. And so he's been working on this for his PhD. It's a very nice journal paper also that gives an overview. I think many of these elements will be recognized today. And then more recently, he joined our lab, and we're looking more at tightening the connections with machine learning, for example, and many more things. And so he also won the ACP Doctoral Award, the honorable mention of that award last year. And so I think it's really nice work, and I'm looking forward to get this that we can hear this overview of that field. So let's all welcome Dimos.
Thank you very much, and thank you a lot for the chance to talk today here. So today's talk is about constraint acquisition, about learning constraint models from data or via interaction with the user. So just a very, very small introduction. Everyone here, I assume that everyone knows what constraint programming is. So it's used in order to solve combinatorial problems in AI. It has applications in many different domains. And the main paradigm used is that the user models the problem as in terms of decision variables, their domains, and their constraints and objective function. It gives the model to the solver, and the solver returns the solution. However, modeling is not always so trivial. It's not that you will give me a real-world combinatorial problem, and I will say, this is a model, let's give it. It's not always trivial, it requires some expertise, and it's considered to be one of the bottlenecks for the wider adoption of CP. So, along guys, many other avenues of research that have been presented in this summer school in the learning to model category. Also, constraint acquisition has been evolved in order to learn the constraints of the problem. Note that in this research area, we learn the structure of the problem. We don't learn the parameters of the objective value or of the constraints or anything. We learn the structure. We learn directly the constraints that are present in the problem. So there are mainly two types of constraint acquisition. We have the passive case, passive acquisition, where the system gives a set of examples to the system, examples of solutions of the problem or non-solutions, cases where we have failed to solve the problem. And then the system returns the model back to the user, and then the user can use it to solve the problem. In the interactive case, in interactive acquisition, the system directly interacts with the user. It's not a passive case where I get the set of examples, I do something, and I give you the model, but the system asks some questions, some queries to the user, and the user has to answer them. Via this interaction, the system is able to return a CSP model when it has converged to the constraint set that models a problem. So let's give some background on constraint acquisition, some terms that we are going to use throughout this presentation. We will repeat them later, and we will give some examples, don't worry. So first of all, we have the variables of the problem. The user has to give the variables of the problem along with their domains. This is called the vocabulary of the problem that we want to model. Along with the vocabulary, the user has to give a constraint language, gamma, that contains the possible relations that can appear in the problem that we have in hand. These are not all the candidate constraints, these are the relations. So, for example, I want to model a Sudoku problem, we will see it in a bit, and the user can give, so I think that there are not equal constraints in there. So you give the relation, and using the language and the variables, the system creates the constraint bias, the set of all the candidate constraints that can appear in the problem by using the relations you gave to all the combinations of variables that it can be used. Based on the candidate constraints, the goal of constraint acquisition is to recognize which of these constraints are part of the set of constraints of the problem and learn them, putting them to CL, the set of learned constraints. based on a set of examples that is given by the user or that is created via the interaction. The goal is to have a learned set of constraints equivalent to the target set of constraints, which is, of course, unknown, but we can check this equivalence with the labels to the examples. Now, let's see. Our running example will be 4x4 Sudoku, so we have an easy running example. In this case, we have the variables of the problem, which is its cell with the indices for row and column. The domains that are 1, 2, 3, 4, that's the values you can put in a 4x4 Sudoku. Assume that the user gave as a constraint language these 4 constraints. The user could also give only the not equal constraint if the user knew that only the not equal appears. But we assume here that the user may not know what constraint relations are the correct ones for this, so he gave more relations in the language. Based on this language, the set of candidate constraints is created, which is basically all the combinations of the above relations to all pairs of variables of the problem. So in the end, after constraint acquisition finishes, we want the learned set of constraints, CL, to be all the not equal constraints in rows, columns, and blocks. Okay, and we have a set of examples that are like this, look like this, are solutions of the problem or non-solutions of the problem with the corresponding label. There is also the alternative, not model it with binary constraints, but model it with global constraints. So in this case, the constraint language would have the all different constraint, maybe also more global constraints in order to recognize which ones are present. And the set of candidates would contain all the all different constraints that can be created in this, with these variables. So in this case, CL ideally will contain all the all different constraints in rows, columns, and blocks. So most constraint acquisition methods are adapting the candidate elimination paradigm from artificial intelligence. So it's basically, you have the full set of candidates. This square is a set of constraints. So this set of constraints is split in 2 parts. The constraints that we want to learn and the constraints that we don't want to learn, that we want to remove from the candidates. So somewhere in the middle, we have the target set of constraints that splits this set into 2 sets. And in the beginning, B, the bias, is the full set of candidates, and CL is typically empty. Of course, if you have some background knowledge, you can initialize CL with some constraints already in order to start from what you know already. So during the acquisition process, constraints are removed from the bias, and the line from B goes down, and constraints are added to CL, and the line of CL goes up. And the goal is to converge to the target set of constraints. When you have a set of constraints that is equivalent to the target set that you recognize from the answers of the user or from the labels, and you cannot change this set of constraints, the set of solutions of this set, by adding more constraints from the candidates, then you have converged. So what do we learn in this case from the examples that we have? Remember that the examples are assignments to the variable of the problem. So an example of a Sudoku would be an assignment of a value to each cell of the Sudoku. So what do we learn from solutions of the problem, called positive examples? So in positive examples, the violated constraints in solutions of the problem, the violated constraints, we know that they cannot be part of the target model of the problem. Why? If they were part of the model of the problem and violated, it would not be a solution. So it is a solution, so these are not part. So in this case, from positive examples, we can remove candidates and get the red line down. On the other hand, from negative examples, non-solutions of the problem, we have the opposite. We know that at least one of the candidate constraints is a conflict that made the user classify this as non-solution. So at least one of these constraints is part of our target model. So we learned something about our target model, and the learned set of constraints goes up. So this was my talk. Thank you very much. This is the small summary. So we discussed why constraint acquisition, what is passive and interactive acquisition, and candidate elimination. I'm kidding, this is not my talk, but I want the section to be a bit interactive, so I already saw a question, and that's the goal. So I will make some small breaks during the talk in order to have questions to discuss before we continue to the next part. Please.
Set of questions, let's call them interactive queries.
Yes.
Can you say why you call it bias? Is there a reason you call it that?
Because it's the bias for the problem. If it does not have a constraint in it, it cannot learn it, so it's biased. It's the set of candidates of that it can learn from, the constraints it can learn from. So if you model it with all different constraints, you can learn only all different ones, and goes on.
So is it more like when you do supervised learning, the bias is I pick a class of models, which is say decision trees. Maybe the thing I need to learn cannot be exactly modeled as a decision tree, so my bias is towards decision tree. Is it in that sense? Because you're assuming that the constraints belong to.
Yeah, my bias is towards the constraints that are in there. Another question, please.
At the beginning, you have a set of candidate constraints, and it correlates with a lot of all different constraints.
Assume.
It's necessary to know it will be all different constraints, or it can work with some constraints and some.
You can give any relations you want, anytime. So you can give, for example, the whole global constraints. We will see in the next section for passive acquisition a method that it actually takes, I think, all the global constraints and tries to find out. But yeah, this creates some problems in some methods. In general, if you give too many and you have 10 millions of constraints, it might be a bit problematic. But yeah, there are methods also we will see that try to tackle that.
Would it be possible to add some variables into our model to be able to reify some of the constraints and verify that the constraint is verified as a variable of our model?
You mean to put auxiliary variables that are refined with the set of candidates? Yes. So that's actually how it's programmed. Where in some cases, we will see in the end, in the third section, I assume. So when you are actually want to find an example and you want to see which constraints of the candidates are violated, that's how it's done.
So would it be possible to, so that would be part of the solution, but you wouldn't be able to use that as part of the model, the concept of reassigning constraints?
If you want to use it as part of the model, in the beginning you have to put it in the variables, in the input variables, yes. I saw another one, yes. You are not sure?
How do you know when to stop? Because, for example, you may face a case maybe where there is a lot of redundant constraints. So, in a way, you will not stop to find new constraints to add to the problem, maybe. So, in that case, occur or not?
So yes, it depends on passive learning or active learning. In passive learning, you have a specified set of examples, so you just go over all of them, and you are done. You may not converge in that case. Maybe the examples are not enough. But on the active learning, we will see in the third section. So there, I have a specific slide for the redundant constraints. That also makes it difficult in some parts. So I'm very happy that we had 4 questions. That's good. That's how I want also to go to the in the whole talk. So feel free also to stop me and ask me any questions, just not in the middle of a sentence. And feel free also to take notes. I have the talk in total in 4 sections. I will make breaks, give a small summary in order to have some discussion. I want everyone to be on the same page when we continue, and also have a 2 minutes break so everyone can a bit calm down and then continue to watch the talk.
Can you say anything about computational complexity of the problem?
It depends on the method, passive or active.
Say
easy, I would say, polynomial. So in case of generating tests, you have just the constraints that you want to test in the set of examples in some different ways, but still it's that. On the interactive case, where you actually have to solve the NP-hard problem of finding an example to ask as a query to the user. So that's different, but there are different complexities also there, how many interactions you want. Yeah, we will discuss in that section. So I'm very happy with the questions. Continue like that, please. So, okay, we gave the small summary. We discussed these things. I will not repeat them. We discussed also the questions. Let's continue now to passive acquisition. So, as I said before, in passive acquisition, we have the labeled examples that are given from the user to the system. An example is an assignment to all the variables of the problem, labeled as a solution. I think it's looking good, okay? Green is looking good, nice. Green, and a non-solution, red. So, using these examples, the passive acquisition system returns the CSP model. There are many different approaches for this. There are approaches that use training classifiers and then converting them to CSP models with some methods. There are data mining methods, version space learning-based methods. All these are statistical approaches. All these are mainly generate and test approaches. We also have a generate and aggregate approach. We will see some of them, not all of them. Of course, we don't have time. So we will see some of them now. So we picked 4 of them, I think, or 5, based in order to check different types of methods. So we have the model seeker, where it can learn global constraints from data. So in model seekers, the language gamma that we discussed consists of global constraints. It actually gets the global constraint catalog. Also, it gets some patterns from the user that is based on domain knowledge of the user that says, for example, for Sudoku, I probably want to check rows, columns, blocks, and stuff like that, or sliding windows. They don't have exactly to be this specific pattern, but it has a set of patterns that is given based on domain knowledge. And based on the patterns and the language gamma, the candidates are generated. Note that not all the possible combinations are generated here for all global constraints, for all different amounts of variables. It could explode exponentially. So in this case, we have the patterns that specify which variables to use in each constraints to generate the candidates. So analyze the candidates. We have the set of examples that consists only of solutions of the problem, only of positive examples in this method. It does not handle non-solutions of the problem. So first, the set of examples is transformed to a convenient form. What does that mean? You have the Sudoku, the 9-to-9 Sudoku. If you give it to the user modeled as 81 variables in one row, it will directly convert it to a 9-by-9 array. So it finds out how to convert the problem in arrays, in shapes, and stuff like that in order to be able to apply the patterns on your problem. So it transforms the set of examples, and then you get the new set of examples and the candidates, and you give it to the constraint seeker. So the baseline is you just test each constraint if it's accepted by all solutions. If a constraint is violated by a solution, then you just remove it. It cannot be a constraint of the model. However, it's actually a bit more than just a violation test. It also tests the density of the set of solutions of each constraint in order to see which one is more preferable, and it prefers actually more dense constraints that have a more dense less set of solutions. And also it ranks them based also on how common they are used in general on CSP problems and many other criteria. And then this set of constraints is given to a dominance check. It checks which constraints are dominated by others. If you have an all different on 3 of the variables of the 4x4 Sudoku, 3 of the variables on a row, and you also have learned the constraint on 4 variables of a row. The one on 4 variables is dominating the other one. So you can just remove the smaller one. So it has a good dominance check, and after this, the set of constraints is proposed to the user based on the ranking that has been made in the previous step, and the user picks which are the constraints that actually exist in this problem. So in the previous case, we saw model seeker that learns only from global constraints. It cannot learn binary constraints. Here we have CONAC from Constraint Acquisition. One of the first approaches, that is a SAT-based version space approach. In this case, we can learn only binary constraints, the decompositions, basically, of the globals, if we have globals. So we have the set of examples and the set of candidates that are given to the system, and the system takes the examples one by one. It tests all the constraints in this example that we have in hand now. It gets the violated ones only, and then it checks if the example is a solution of the problem, then we remove this set of constraints from the candidate set, as we discussed before. If it's not a constraint, if it's not a solution, of the problem, the example, then we add the disjunction of the constraints violated to CL. So we know at least one of them is satisfied, so is a constraint of the problem. So we say or this, or this, or this, or this. So while it continues and it goes through this loop for all the examples in the training set, it also removes constraints from the disjunctions that it have added when it removes them also from the bias. When it removes a constraint, it says, this candidate cannot be part of my set of constraints, so it removes it also from the disjunctions, and if you have enough examples, the disjunctions become smaller and smaller. In the end, when the examples finish, you have some disjunctions and stuff like that, so this is our version space in the end, the combinations of all the constraints in the disjunctions in CL. It has some criteria in order to pick the more specific or most generic set of constraints based on the set of solutions that they have. So we saw an exact approach, CONAC, based on version spaces, and model seeker learning global constraints. These methods are not robust. If you have an error in your labeling, if you say that a solution is not a solution of the problem, or a non-solution is a solution, then you are done. Then you have removed some constraints without any reason, or you have learned some constraints without any reason. So we now go to the statistical approaches that are robust and can handle noise in the training set. So we get the set of examples and the candidate set. We create a new set of examples based on this, which is basically, in this method, by Yesak, I forgot to mention it, yes. We transform the set of constraints, and now instead of features, in the features, instead of having the variables of the problem and the assignments, you have the constraints that are in the candidate set and a Boolean value 0 or 1 if the constraint is violated or not. And now you are only going to use the new set of examples and throw the assignments. So you train a naive Bayes classifier based on this training set, and based on and using the naive Bayes classifier, it's basically a counting method, counts in how many examples a constraint is violated, positive examples and negative examples. You can derive the probabilities for a constraint to be violated in a solution of the problem, and the probability for a constraint to be violated in a non-solution of the problem. So you can use these probabilities in order to say, okay, this constraint is violated more often in solutions than non-solutions of the problem, so it's probably, I don't need it, it's not a constraint of my problem, or the opposite. You have a threshold here in order to find out which constraints to add and which constraints to remove. Usually the differences are massive. If a constraint is not a constraint of the problem, it has very low output if a constraint is a constraint of the problem, if a candidate is a constraint of the problem, it has a very high value. So the threshold is not affecting too much the performance. So we have one more statistical approach that is similar to this. It has a counting part, but is not actually training a classifier. It counts directly the violations of in solutions and non-solutions, and it uses a sequential analysis-based approach in order to learn the constraints or not. Why that? Because if you have tons of candidates and tons of examples, you don't want to actually check every constraint in every example to get the final counting. So this speeds up the process by a lot. So you get the set of examples and the set of candidates, and you also get two more values, two more parameters, A and R. We will see in a bit what they do. So you take all the candidates one by one, and you take then, after you take one candidate, all the examples one by one. You test the constraint in the example. So, sorry, with this way, you don't have to represent all the set of candidates at once. If you have 5 million candidates, you can just generate them one by one, because you use them one by one. So you test the candidate in the example, and then you just use two counters, which you increase if the constraint is violated in an example that is a solution of the problem, the first one, and the second one, you just increase it just if it's violated. So using these two counters, you know basically the percentage of violations in solutions or in general. Using these two counters, now you can just, it's a very simple idea here, you can just say, if my counter of this constraint violated in solution of the problem is too high, then probably it's not a constraint of my problem, so just remove it. So how is this too high defined? With the parameter R that the user gave. So you have 10,000 solutions, 10,000 examples in the problem. You just give a parameter saying, if it's violated in 500 solutions, I don't want the constraint. So if it's not dismissed, then you can add it to CL if it's violated in a number of non-solutions of the problem. So if it's violated in most non-solutions of the problem, then probably it's a conflict, so you can add it to your CL. After you go through all the examples, if you have not stopped in the middle to add it or remove it, then you can just remove this from the set of candidates. If you have not learned it while you go, if it's not violated in enough non-solutions of the problem, just remove it and go to the next one. So this part is based on the sequential probability ratio test from statistics. So after you are done, you remove or you add the constraint, you go back, you generate the next constraint, and you go through the examples once more. So all these methods that we saw until now are generate and test approach. Generate candidates, test them in different ways in the set of examples, and then see if you add it, if you learn it, or you remove it. So this method is a generate and aggregate method. So what does it mean? So it learns constraints of the following form. It has an expression, and it tries to learn the lower and upper bound of the expression, numerical expression. So the goal here is not to learn a constraint, but to aggregate the bounds of the expression based on the set of solutions. Again, this method only uses a set of solutions of the problem and not non-solutions. So the goal is to aggregate the bounds. So in this case also, the language gamma contains only numerical expressions and not constraints, not Boolean expressions. You cannot give it the not equal constraint, the greater than, and goes on. You just give it a set of expressions, for example, one variable minus another variable, one variable plus another variable, the absolute value of one variable minus another variable, and goes on. Based on these expressions, based on the bounds, this can also model binary Boolean constraints. For example, if you want to learn the 4x4 Sudoku. You're going to learn not equal constraints. What a not equal constraint means in this case, the absolute value of one variable minus the other variable is greater than 0. So in this case, you can learn the not equal constraint, also many other types of constraints, or basically most types of constraints that are used. So you take the expressions in the gamma one by one, and you generate all the expressions, all the expressions that can be generated for all sets of variables for this relation. Then you aggregate the bounds. So you take, for example, the absolute value of x1 minus x2, and you see what's the lowest value in our data set that this can take, and what's the maximum value in our data set that this can take. So you get the bounds for this expression. After you aggregate the bounds, then you try to generalize to first order constraint. Again, this is pattern-based, like what we saw in the model seeker. So you know that you have to look for patterns on a row, and then you say, okay, let's check. Have I learned all the expressions, or all the expressions in this row? Do they have a similar bound? Absolute value of x1 minus x2 is greater than 0 in all cases in this row. If yes, then I can generalize it to a first order constraint. And you try to generalize everything that you have learned. And then you try to see if the bounds that you have learned, generalizing to first order constraints, if they can be expressed using symbolic expressions. So one symbolic expression that is used is the 0, that represents the not equal part, but it can also be the number of rows, the number of columns of the problem, or other input that the user has gave. When you learn a nurse rostering problem, for example, the bound does not depend on the rows or anything, but it depends on the number of shifts that that hospital must have, the minimum number of shifts. So you must know the minimum number of shifts the hospital must have, and then you see, this bound can be expressed with that. This way, you can generalize to different instances of the problem, because in one instance, in one hospital, you have a different minimum number of shifts than other hospitals. So after you do also this step, you filter constraints that seem useless, that have not been generalized or are too trivial and stuff like that, and you have the final set of constraints in the form of expressions. So again, a small summary. We discussed passive acquisition, how it works in general. We saw different approaches for passive acquisition. We saw how to learn global and fixed arity constraint, and how to generalize to third order constraints using expressions. It's time for questions before we continue on the interactive part.
You can go back to the CP count. I have a high-level question. So I'm trying to see if there's a relationship between constraint acquisition in this setting and cutting planes in, say, binary linear programming. Okay? So there, I give you a bunch of linear, say, inequality equality constraints that express what I think is the feasible region. Now, usually that feasible region contains points which are not integer points, and in cutting planes, I want to add constraints that cut off non-integer points. Ideal case, I get the convex hull of the integer points, in which case that's the tightest possible representation of the integer feasible set.
Yeah.
And I can get lots of examples. I can sample lots of integer points. I can solve linear programming relaxations, whatever. So I can create examples. Okay? But there are some techniques, mathematical, that use the structure of the polytope to derive cuts. But here, if cuts are just linear inequalities, that seem to be a subset of what you can represent.
Yeah.
If anybody has noticed that connection, I mean, it seems like one-to-one.
Yeah, I'm not sure. So here, one of the authors of the paper is Tias. So we can discuss in coffee break. I would say, so intuitively, I will say yes. It's also based on the count OR method. So intuitively, I will say yes, but I think we can discuss it more in the coffee break. Go. Yeah.
These are also non-complex expressions, but you can think of it as trying to find that complex sum. So anything that cuts over
There's some team to try it in the hackathon. Yes? Yeah, yeah, that's good. So, I like very much how it's going. Please ask more. That's actually a very good question, how to choose which method to use. So in Model Seeker, for example, is more trivial. It learns global constraints. When you want to learn global constraints, you use Model Seeker based. The other methods, it depends on what you want to learn, what constraints you want to learn. It depends if you have noise in your dataset. If you expect to have some noise in your dataset, you go directly to the statistical approaches. And actually, you directly go to sequential acquisition, which is basically an extension of the previous Bayes ACK. If you don't have noise, then you go to Model Seeker to learn global constraints, to CountCP to learn first-order constraints. It depends also if you want to generalize to different instances of the same problem. CountCP can do that. You can learn that this constraint is based on the symbolic bound number of shifts of the hospital. The other methods just return a constraint using a specific value. So, yeah.
I was wondering if any of the methods is also able to learn effective function, or is this only applicable to constraints?
So constraint acquisition is basically only to constraints, to the hard constraints part of the problem. There are some works, but it's mostly a different field. Yes, that's an issue, and it's an open challenge in general for constraint acquisition. For example, to learn nested expressions and stuff like that. Yeah, it's an open challenge that is, I think, quite important avenue for future work. So yes, again, we have more questions. That's very good. Let's continue like that, and let's continue also after the talk like that. It's great. So now we discussed passive acquisition and some methods. Let's go now to the interactive part. So in interactive acquisition, you have an oracle interacting with the acquisition system. The most common interaction is the acquisition system to post unlabeled examples to the oracle, and the oracle labels them, the user, let's say, labels them as this is a solution, this is not a solution of my problem. So how these queries, these questions look like. So we have the name is membership query. It's from early days of AI in the active learning paradigm. So we have this question, for example. You post this Sudoku to the user, and the user has to answer. And we also have partial queries where some variables are not assigned in the problem. You have just some of the variables assigned, and the user has to say if it's OK or if it has a problematic part. So in this case, in both these queries, the answer is negative because some constraints are violated. So what are the challenges for interactive constraint acquisition? Of course, besides learning the correct set of constraints. So the challenges are, first of all, to have a minimum number of queries. You cannot have a user on the other side of your screen and tell him, OK, today you have to answer 10,000 questions. Nobody will do that. So this is a very important challenge. And the second one is to have a minimum waiting time for the user. You cannot have the user on the other side of your screen just waiting to load in order to get the next query. When you open your browser, if it takes 5 seconds, you close your computer, right? It's annoying. You cannot have the user to just wait 5 seconds, 3 seconds for every query. It has to happen almost instantly. Let's say 1 second. So, how it works. First, you generate an example, an assignment to the variables of the problem. Then, after the example is found, you post it as a query to the user, and you get the answer of the user. Based on the answer of the user, you update your version space. You update your set of candidates or your learned set of constraints. So, in the case of the positive answer, you shrink the version space, you remove violated constraints from bias. And in the case of a negative answer, you try to find more constraints, which of these constraints are the real conflict. You try to zoom in violated constraint scopes using partial queries and find out which one of them was the conflict that made the user to answer negatively. After you update your version space, you go back, you generate a new example, and you do this process again and again until you cannot generate an example, which means that it has converged. When you can't generate an example that can give you some information, we will see in a bit, then the system says, OK, I'm done. Here is your set of constraints. So these are examples of queries that are posted to the user in our system, and the answer below. So in this case, it's a positive answer. It's a Sudoku of the problem. It's a Sudoku that is a solution of the problem, as you can see here. So my answer was yes. And we can eliminate candidates. It's in the green part. Here we have a negative answer. It's not a Sudoku. We can see many different constraints violated. So the answer is no, and we are in the red part. So we will take this one by one. Let's start with query generation. It's a very important part. So you must generate an informative query, an informative example. So whichever of the answer of whatever the answer of the user is, yes or no, you can get some information from that answer. Also, you want to get the maximum amount of information that you can. So the quality of the query matters. You cannot just take a random example and give it to the user and say, OK, I learned something for one constraint. You want to get the highest amount of information. So what finding an informative query means? We want to find a non-redundant query. What is a redundant query? A query that I will ask you, you will answer me, and I did not learn anything more. So we want to always include information in the query. What that means that we have to not violate any learned constraint that we already have learned. If we violate any constraint we know is in the model, we know that the answer will be no. So no point to ask it. And we also want to violate at least one constraint from the candidates. So we want basically to solve this CSP. And that's the NP hard part that we discussed before. So why do we want to violate at least one constraint from the bias? Because that's, OK, we want to satisfy all the learned constraints. That's clear. But why we want to violate at least one from the candidates? Remember what we learned from the examples. This is the slide we saw before in the beginning. So when learning from positive examples, I know that some constraints of the candidates can be removed. And when learning from negative examples, I know that one of the violated candidates, at least one of the violated candidates, is part of my problem. So in both cases, the information we get is about the violated candidates, not the satisfied ones. So I want to actually violate candidates in order to get information from the answer of the user. So if the user answers it is a solution of the problem, I shrink the set of candidates. If the user says it's not a solution of the problem, I will try to find one violated constraint. So we discussed what an informative query means. So let's now see the second part, the quality of the query. So we said better generated examples lead to faster convergence, and more information per query will lead to actually to less queries needed in the end, less interactions. So typically, what is used here is, during the query generation part, is this objective function, to try to maximize the violations of constraints that are in the candidate set. It's not fully aligned with the goal, but I will give now the intuition. Assume that you have 10,000 candidates, and you generate examples that violate them one by one. You need 10,000 questions in order to eliminate all of them, if the answer is positive, of course, from the user. On the other case, if you have 10,000 candidates and you violate them all in the same example, you need one question to remove them. So one question, 10,000 questions, quite important to try to actually align with the goal of query generation. So let's go now to the last part of convergence. Finding an irredundant query is not always easy. We discussed the constraints, the objective function of that part, but although it might seem easy, it's not an easy CSP. First of all, set of candidates can be huge. You will not have only 100 candidates. The set of candidates will be really huge in your problems. This can slow down the query generation process. Second part is the implied constraints, the redundant constraints. Some constraints in the set of candidates can be implied by other constraints. So, for example, in the 9-to-9 Sudoku, you have all the constraints, not equal constraints between any two variables in the rows, columns, and blocks. So, 648 constraints of them imply the rest 162 not equal constraints. If you learn the 648 constraints first, then you cannot violate the rest. You can't violate them. So this process of trying to find an example satisfying what I have learned, violating at least one candidate, cannot succeed. It cannot find an example succeeding that. So someone will say, yes, we will converge because we cannot generate an informative example. But yeah, we will converge after 10 days. Why? Because indirect implications are not detected with propagations. If an implication is direct, if an implication is, I have the x1 greater than x2, and I have the other constraint x1 not equal than x2, okay, one implies the other directly, you can directly identify it. But if it's on different variable sets and combinations of constraints implying others, you cannot detect it with propagation. So you actually have to try to learn them in some way in order to converge, in order to end up with a very small or empty set of candidates and then converge. In order to do that, custom solvers are often used in order to try to find partial examples in the beginning. So instead of trying to find a complete assignment to the variables of the problem, you try to find a partial assignment. So the difference of these custom solvers with conventional solvers is that instead of returning an example only in leaf nodes of the search tree, only when all the variables are assigned, they can return examples in any node of the search tree with only 5 or 10 or 20 variables assigned just to satisfy this property. Satisfy the constraints that you have learned that are in this set of variables, and violate at least one candidate. And then you can return a partial solution and post it to the user, avoiding the indirect implications. Recently, a method for conventional solvers was proposed, a projection-based query generation, where you use the same intuition, but instead you say, in conventional solvers, you cannot return an assignment in an arbitrary amount of variables. You have to specify the variables that you return a solution on. So how to avoid indirect implications there? We get information only for constraints in the candidate set. So let's just use the variables that participate in these constraints. So in our Sudoku case that we said with the 162 constraints, we will only use variables from these constraints that participate there. And that way, some other variables will not be part of our example. So indirect implications from constraints in these variables are avoided, and we can now actually continue the learning process until we converge. So we discussed all this was from that part, generate example. So we discussed this, what happens after query generation. We ask the example to the user, we get the answer. If the answer is positive, we eliminate the candidate constraints from, that are violated. What happens when the answer is negative? How do we actually learn constraints? So it's basically a two-step process. First, try to find the scope of the constraint, and after you find the scope of the constraint, try to find the relation of the constraint. So we have the find scope and find C parts, where again you ask queries to the user, simpler queries though, partial ones. In find scope, you exploit partial sub-queries. So you take the previous example that you had, you remove some assignments, and you repost it to the user. If the answer of the user changed, then you know that the removed assignments, the removed variables, were problematic. One or more of the removed variables contained a problematic part. So one or more of the removed variables are in the scope of the constraint. We can, let's say, we can see it here. So we have the full example with m variables, and we try to decompose this example by removing parts of the problem, and we ask the query again and again. If the answer of the user from negative, from no, it's not a solution, becomes positive, then we say, oh, stop here. We know now something for the lastly removed variables. So let's go up to these variables and add more variables again to the problem to find out which one is the problematic. Don't worry, I know some are confused. Let's see it with an example. 4x4 Sudoku. We have here the Sudoku. I have read the variables that participate in constraints that are violated. The answer of the user is negative. No, it's not a solution. Remove some variables. Is it okay now? No. Remove some variables. Is it okay now? No. Remove some variables. Is it okay now? Yes. It does not violate any constraint now. What do I know? One of these lastly removed variables are one of these is part of the problem. It's part of the scope of the constraint. So let's add one of them to find out which one is the problematic. Is it okay? Yes, it's okay. So I just directly know that this variable is in the scope of a violated constraint. So I learn this variable, and I continue with this process in order to find out this variable again and find the whole scope of the constraint. So after this process finishes, I know that these two variables are violating a constraint of the problem right now. So what I do, I try to find out which constraint of the problem. Assume that we have these constraints in the candidates for this scope. Which one of them is it? How do I know? Try different assignments in the specific scope to find the specific constraint of the scope. Is it okay? Yes. So remove this constraint. It's violated in this example. Is it okay? Yes. Remove this constraint. So now only this constraint is left from the candidates. So we directly learn it because we knew one of them was violating a constraint of the user. So now we learned also the constraint. First, we learned the scope of the constraint, and now the constraint. So there are many different algorithms for these approaches. We will see basically categories for these algorithms. One of the state-of-the-art is QAC, not from the DAC, from quick acquisition. So this algorithm learns a violated constraint here, one violated constraint here, per example that is generated, and then returns back. It's exactly the template that we saw. The strong part of this algorithm was that it learns a constraint in a logarithmic number of queries. There were other methods that needed a linear number of queries, which was quite more in practice, quite much more. So there is also multiple acquisition, where the difference is this line, instead of going to generate example, it goes here. Why it goes here? So we noticed that you have the example, you learn one constraint. Let's go a bit here. We learned this constraint, but there are more constraints that I can learn from this example, right? So why don't get a partial example from this by removing the violated constraint from this, so it does not affect the answer of the user, and try to learn more constraints from this example instead of going back to generate a new one. Yes, in 4x4 Sudoku, it's very easy to find an example. It's not always that fast. You don't want to have the user waiting. So you can just go remove some parts of the problem to not contain the violate constraint you have learned and ask again here. And you only go back to generate example when you get a yes answer, when you know that there is nothing else to learn in here. We saw some approaches for interactive acquisition, but one of the important questions that some of you will have is, what if the set of candidates is too large? Do I have to specify exactly the language on what constraints it contains, the problem will contain, or can I put 5 million constraints in my set of candidates so I will be safe? I will probably find out what I want. So, yes, I can, although in the previous methods we saw we couldn't. We could not store all the candidates, or even if we could, query generation would be very slow. Assume you give 5 million soft constraints, 5 million constraints refined in the solver, and say, find a solution violating one of them. It's crazy. So in the previous method, we could not, but now we can. With growing acquisition, all of the algorithms constraint acquisition have a very weird name. I know, Quack, Multi-Acq, Grow-Acq. It's easy to remember, though, because it's funny. So in this approach, basically, it's a bottom-up approach. It's a meta-algorithm. It uses the previous approach in a bottom-up fashion. So you have the interactive CA algorithm. This square is the whole previous thing, the whole previous template that we saw. So you have this. You start with a small subset of the variables, or with the empty set. You learn what you can learn from there, and then you say, OK, add one more variable. If I am still in a subset of variables, add one more variable on this set. Then you generate the bias, the set of candidates, containing only this new variable. So you generate a part of the candidates in each time, containing the new information that you want to get based on the new variable that you added in the problem. So you start, for example, in the 4x4 Sudoku with the block of 4, with one block. You learn what you can learn there, and then you add one more variable. And you try to find out which constraints contain this newly added variable. You generate part of the bias in each time. You get also the previously learned set of constraints to use it in query generation. And you do this until, in a loop, until you have considered all of the variables of the problem where you converge. So this, besides being able to handle large set of candidates, because you consider only a few constraints in each step, it saves time during query generation. And we can use this very, very, very precious 1 second we have to generate a query in order to guide better constraint acquisition, which will be the next section that we will see. Now, we discussed how interactive constraint acquisition works, how query generation works, and how to find the scope and the relation of the constraints. And also, we discussed growing acquisition that gives us a lot more possibilities to use constraint acquisition with large sets of candidates. It's time for many questions. Yes, so we will discuss it in the end in the challenges. You are right. It's one of the most important challenges, noisy answers. So there are some works for giving the user the possibility to answer, I don't know, and then from that, learn what the user does not know in order to guide also your queries later. It needs to know what's the problematic part, basically. Not the constraints exactly, but if the user does not know anything about the problem, he cannot teach anyone about the problem, right? Yeah.
What if we don't know the answer because there are
So you can give it to a simulator. So there are some works that I have discussed with some people that are simulators that can answer this query for you. Previous systems, for example, of the that can used to solve the problem that are not CP based, and then you want to convert them. Please.
Is it more interesting to try to generate some wrong example or true example?
Very nice question. It's a very good assist for my next part. But yes, it's a very good question that we will discuss exactly that.
Let's say that you're a very good modelizator or modeler, I would say, in CP. You know the problem. And at some point, you were talking about the fact that indirect implication is not known by propagation. I suppose that's why we use global constraints at some point. So with constraint acquisition, is that possible to discover a problem where we should build a new global constraint because the convergence is too slow with, I would say, different, only less different principle, stuff like that. You see what I mean?
Yes. So what I understand is to be able to generalize from what you have learned into global constraints, right?
Yeah, because you told us that if the convergence is too slow, it means that we have indirect implication. And I understand that as we need a global constraint to spot that indirect implication between variables. So does it mean that we can discover new global constraints?
Actu-
We need the global constraints for the optimization.
yes, actually, also global constraints imply other globals. So in the Sudoku problem, there are 27, I would guess, global constraints. 2 of them are implied by the rest of them. So you again have this problem. Okay, it's easier to find the 2 than the 162, but yes. So you say that I did not understand actually the real thing. So you want to generalize and learn more global constraints and be able to detect future global constraints you are going to learn. So I learned one constraint in a row, and then I will say, okay, probably there are in the next row too, right?
Let's say that if we take the same problem with 2 different languages. The first one is only basic symbols, like less different, equal, something like that. And the second one is
All different.
global constraint plus the basic operator. If we spot a difference in the convergence of the both algorithms with the same example, does it mean that in fact one lacks global constraints?
One?
One lacks the global constraints operator between the variables.
Yes. So one also.
So it means that we need a new global constraints for that particular problem.
Yes. So in general, in constraint acquisition, we need, in interactive constraint acquisition, we need to be able to learn global constraints, because it's not yet the case. So you can learn global constraints with passive, but not with interactive. So using the GROWAC method, this thing, you are now able to learn problems with large sets of candidates. Global constraints lead to large set of candidates because they don't have a fixed arity. We don't know how many variables are involved there. So this explodes exponentially the set of candidates, but with this method we can handle larger candidates. But there are also, for some global constraints, some other issues regarding some assumptions. So many global constraints cannot be learned, but so in general, I will say that for all the questions, I'm very happy with the questions, because it means that people understand what we are saying here very well, because actually all the questions are related to next parts. So some questions are related to the guiding constraint acquisition, which is the next section, and many questions relate to the open challenges that we have, global constraints, noisy answers, and stuff like that. So it's a very nice thing. Please. No, seriously, I'm laughing because it's included later. Yeah. So yes, I'm very happy about this. Yes. So the short question, the short thing is, let's wait 10 minutes. So now we created anticipation, right? Okay, let's see. So we made the summary. We discussed many things. I'm very happy with all the questions. So now let's see how to guide constraint acquisition, interactive constraint acquisition, how to decide what query to answer next. If we want to remove constraints first and ask M for positive queries, positive answers from the user, or from negative ones, and how to do that. So we discussed about the quality of the query. If we want less queries, we want to have more information per query, and typically we maximize the violations. So maximize the violations means that we will probably get negative answers in the beginning, learn some constraints, and when we learn the constraints, we get the positive answers in the end to shrink the candidates. This does not fully align with the goal, though. And now let's see why. So indeed, when we will get a positive answer, we want to maximize the violations of constraints with the example generated. The example generated is E. So when we aim for a positive answer, we want to violate more, because the more we have, the more we will remove. What happens, though, in case the user answers negatively, labels it as non-solution of the problem? So in this case, the less constraints we violate, the easier it is to find which one of them is the real conflict. So again, assume two extreme cases. One extreme case that I generate an example violating only one constraint. If the user answers, this is not a solution of my problem, I actually don't need the find scope and find C parts. I directly know this is the constraint, I learn it with 0 queries. Assume now that I violate 10,000 constraints with one query. The user answers no, and I now know that, oh my God, one of these 10,000 constraints I have to learn. So I have to find out which one of them. Many queries needed. So this is also quite important. But there is a problem here. Do you see it? It's the exact opposite objective functions for query generation, and it's based on the future answer of the user. So I have to decide what to do now based on the future. It's not always easy, right? We cannot know the answer of the user before we ask the query. So until now, we just said, OK, just maximize violation and see what happens. But what if we can predict if a candidate constraint is a constraint of the problem or not? And so we can predict if the query we generated will be probably be classified as positive or negative by the user. So we have here the goals. To remember them, we will have them here in the next slides. And the question we just asked, what if we can predict? So assume that we have, for now, assume that we already have an oracle O that can tell us if a constraint is a constraint of our problem, the constraint we have to learn, or a constraint we have to remove from the candidates. Assume we already have access to an oracle that can tell us that. Yes, if we had access to such an oracle, we would not need constraint acquisition, but we will discuss later what we will use for the oracle. So in this case, when you have the oracle, so this objective function, don't be confused, I will explain it step by step, but basically it does this. If the oracle says, this is yes, this is a constraint of the problem, M to satisfy the constraint. If the oracle says, no, this is not a constraint of the problem, M to violate it. Why do we want to do that? We aim for positive answers first, maximizing the violations from the bias, from the candidates, but without violating the probably true constraints. So aim for a positive answer that shrinks the bias, the set of candidates, as much as possible. So after you shrink the bias, at some point you will be left only with constraints that you have to learn. So in this case, you want to minimize violations. When you are left by only with constraints you have to learn, you want to violate them one by one to only need one query for each one. Not need more queries to find the scope, find the relation, and spend more time on that. So this is done with this objective function. Let's see it. So we split it in 3 parts. The first part is if the constraint is violated by E, is not in the solution set of the example. So, sorry, if the example is not in the solution set of the constraint. So, if yes, if it is violated, add 1 to the objective function. If it's violated though, and the oracle says yes, it is a constraint of the problem, then punish it. So remove a significant amount of from the value of the objective function in order to say, now this reduces the objective function, don't violate it. So increase when violated, but decrease significantly when it's a probably true constraint. The gamma here is the size of the language. Why it's gamma here? Assume that I have 10 relations per scope of the problem. So if I have a lower amount, then our query generation can say, okay, I prefer to violate these 9 constraints that are probably false, and also violate this one, because I get a bigger reward. So in order to avoid that, you have the size of gamma. Here it can also be far larger, but just greater or equal than gamma. So we discussed how to guide query generation in order to get more information per query. Now, constraint acquisition has 3 layers where we ask questions to the user. Top-level query generation, finding the scope, and finding the relation. Can we guide also the other parts? The answer is yes, and the answer is use the same logic, exactly. The same objective function, slightly modified. So when you try to find the scope, you don't change assignments. You don't pick assignments to the variables. You just pick which variables to include. We said before, remove some variables and ask again, but how do you decide which variables to keep in the next example and which variable assignments to remove? So we can decide it through here. It's the same objective function, as you can see here, but instead of putting assignments to the variables, you just decide which assignments to keep. And also, exactly the same for finding the relation of the constraint. It's the same objective function, with the only difference is that it's specifically in the scope that we try to find out which constraint exists there. So using this logic, aim to violate the probably false constraints and satisfy the probably true constraints, we can guide query generation in order to reduce the number of queries. But until now, we assume that we have an oracle that can tell us that, which constraint is probably true and which constraint is not. Do we have one? So the oracle classifies a candidate as a problem, a constraint, or not. That gives a hint, I know. So until now, query generation, generate the query, learned from the user answers what we could learn, go back, generate a new, and do that again and again. So now we want to use an oracle. How can you use it? It's a prediction problem. You can use machine learning, right? And put machine learning here, give the output of the machine learning, the predictions, generate the query, learn from user answers, update what you know in your data set, and go back to machine learning and continue this loop. Predictions, though, are for constraints, not for variable assignments. note that we don't have now a set of examples of assignments to the variables of the problem. We don't care to classify examples with the oracle. We care to classify constraints as true or not, Boolean classifications. So our data set are the constraints now. The constraints that we learn or the constraints that we remove. The constraints that we know are part of the problem or not. And this data set is constructed during the acquisition process. Every time the user answers us something, we get an information about some constraint, and we update the data set. So when a constraint is learned, at the positive instance, and when a constraint is removed, at the negative instance. How to define, to define a constraint using features, though? You can use the relation of the constraint. It's not equal constraint. It has a constant or not. What is the value of the constant? You have a job shop scheduling problem with the start plus duration equals end. It has a constant. What is the value of the constant? Stuff like that. And you learn, based on that, what's the more common. And you also have scope-based features. Are the variables in the same row? Are the variables in the same column? What is the distance of the variables in these dimensions? And stuff like that. So based on that, you can directly find out that in the Sudoku, if I have variables in the same row, it's a constraint of the problem. Variables after you learn the first constraints, you can directly train a classifier to do that. So an example for the 4x4 Sudoku here. Here are the relation-based features and the scope-based features. We have two values because we have two dimensions. So this is a constraint. Do they have the same first dimension? True, they are in the same row. Same second dimension? False, no. And it goes like that. So then we can use these features to detect based on where the variable is in our array, if there exists a constraint or not, and of course, which constraint. So we construct this data set, and then we can use machine learning as the oracle. So the oracle classifies. What are we going to use? Classification. You can use any classification technique to simulate the oracle. You can say the oracle, replace the oracle with the class of the constraint, the predicted class of the constraint. Just a classifier.predict. So is this enough? Someone would say yes. The first intuition is yes, it's good enough. But why don't use probabilities? Why treat a constraint with 1% probability to be a true constraint and another constraint with 45%? Why treat them the same? They are not the same. So you have to find out which constraints to treat as true constraints. So the goal is to minimize the expected number of queries, right? That's the goal. We don't actually want to predict constraints. We want to minimize the number of queries because the user will give us the final verification if a constraint is a part of our problem or not. So we want to minimize the number of queries. And this is the complexity, the number of queries needed to find a constraint, the scope of a constraint and a constraint after a negative answer, the find scope part. So we say that 1 divided by this is the percentage of queries resulting on a constraint learned. Also, the percentage of constraints, or the probability of a constraint, is the percentage of queries of constraints with this probability that will result on learning a constraint. We just want this to be higher than this. And this is a classifier predict proba in Python. So using the predict probabilities instead of class has been shown to work way better, like 60% of the queries, 50% of the queries. Assuming that a candidate constraint of the problem is, a candidate is a constraint of the problem, even if the probability is less than 50%, can minimize the number of queries to converge. So let's go to open challenges. And we are finishing soon. We are arriving to Elias' question in a bit. So open challenges. We want to minimize the number of queries, right? We want to have a number of queries that does not annoy a human user. So still, it's quite large, the number of queries. The goal, and the open challenge here is to be able to generalize There are some works for that, but in an infant stage. So you want to be able to generalize and ask also more expressive type of queries in order to learn things, to learn basically more constraints than one with each query, to be able to learn more information. Also, one challenge is to be able to learn specific classes of constraints more efficiently. To be able to learn global constraints, first of all, and also linear inequalities and other classes. So there need specialized methods in order to be able to need specialized classes of constraints. And last challenge, very important, it's your question, noisy answers. I have a user that says no, but it should be a yes, or the opposite. I'm done there. I have removed constraints without any reason, and now I cannot learn them. So we have to have a tighter integration with more modern machine learning techniques in order to be able to revert that, to have a more robust approaches. So, some conclusions from the part that we discussed here. We will not make a break here because we have to continue. What is the future of constraint acquisition? What is the future of modeling the problem? We want to acquire the problem, the model from text description and with interaction with the user directly, but not only by asking, is this solution of a problem? Yes. Is it a solution? No. Is this a solution? Yes. It's a kind of boring at some points, right? So you also want to explore the recent advances in large language models, in using natural language for optimization. Can we use this technology to acquire models directly from text description and then refine this model using the user? The answer is, Elias, you are not. The answer is yes. So we split the problem into different parts. So this is the modeling of the problem done by LLMs or other methods that can be used there. And we split the problem to 4 parts. First, it's the named entity recognition. Recognize in the text which are the variables, the domains, the constraints, and the objective value of the problem. Connect the constraints with the variables. Find the relations of the constraints and the variables and the objective value and stuff like that. Which variables participate in which constraint based on the text. Formulate it in a mathematical form. Get the model, and then translate it to a language, to a constraint language, like a modeling language, like CPMPy, Minizinc, and goes on. So this needs to be split in 4 different subtasks, because try to give ChatGPT something very complicated to do, it will fail. But if you give it subtasks, not only ChatGPT, in general large language models, and there are also specialized techniques for some of these parts. For example, there are too many works on named entity recognition with very, very good results, using also large language models and other techniques. So you can use also different things in each part, different methods. And you get the output, the variables and the constraints from this, and you give it to this, then you get the output, and you continue like that until you reach the final model, the translation to a language. You debug the translation automatically. So, for example, you have GPT, extract a Python code, try to compile and run it. If it does not run and it returns an error code, give it back until it runs. This is an automated process. And then you want to refine the model. So here is the interactive part, where the user and the system have to interact in order to refine the solution, learn more constraints during the process. Maybe the system did not detect all the constraints, or maybe the system or the user had some problems in the formulation, and you want to actually, and it's actually unsatisfiable, what we learned until now, and we want to find out what is the unsatisfied part, and based on interaction, refine the model. So some early works on this have a very nice results. So we have a system doing the previous thing. Assume you give it this description. I have 10 hours to spend in 11, again, Belgian problems, right? I have 10 hours to spend in 11. I can see only a small number of attractions in the city, and goes on and goes on. Basically, it's an abstract problem without specifying it. And we have the formulation and the translation, right? Mathematical formulation, and then translate it to a modeling language. So the first output is this. It directly recognized the parameters, the variables, the constraints, and the objective function in a very nice way. And the translation resulted in this model in CP and Pi, which if you actually copy-paste it and run it, it runs very smoothly. You can actually decide what attractions to see today in your last day in 11 using this model. So of course, if there was a problem, if some constraints were not detected and goes on, this continues in an interactive way. This is now the holy grail too, to be able to recognize, to be able to model from text description and refine via interaction. We have reached, based on our opinion, the holy grail 1, which was state the problem, and then the computer is used to solve it, with all the nice constraint languages that we have. So now we have to go this way. Thank you very much. We discussed many things today. I hope you have left some questions for the end. It's a good question if you want to use, so the question is for the recording, if you want to use previously generated examples in order to either modify them a bit for the new example or go to the opposite part. So it's a good question. Usually, query generation does not use previous examples. It only use information for the candidate set and the oracle, the predictions for that. So it could be a good avenue to explore. It has not been explored until now, or how to use the previous examples. It depends on what is the goal. It depends on what is the goal. So if the goal is to minimize the number of generated queries, the number of times that you go in the first part, yes, because you will just learn everything from this. But in this case, you will need to ask partial sub-queries in order to find out each constraint separately, right? And it will lead to more interactions with the user than actually asking a query that violates only one of them each time and generating again and again. So what I say will take a lot more time, generation of the query again and again and again, but the actual number of interactions will be less. So it depends, I would say, if the oracle, the one answering, is a human user or a system simulating.
All right. I think, thank you very much for being with us.
Thank you very much.